All right, hang on tight, because here comes a precise definition of limit, the formal definition of limit. Okay, this is probably the conceptually most difficult section in this giant calculus book. We've tried to motivate this in section 2.1, talking about tangent lines to a curve. We've tried to make it informal and have a way of visualizing it in section 2.2. Now we're going to formalize it. Underlying all this should be that, in particular, those previous ideas from section 2.2. The graph looks like it's trying to pass through a point when a limit exists. Stand by that. We'll talk about it some more in this section too. Okay, so the plan is to give a mathematically rigorous definition of the limit of a function. We'll comment how the informal ideas that we've seen, them trying to pass through a point, Dr. Bob's anthropomorphic definition, how that fits in with the formal ideas. This is so fundamental. The concept of a limit is the idea behind all of calculus. Now, some of the good news is you may be able to fake it and perform mechanical manipulations, calculate limits, calculate derivatives without a deep understanding of what's going on. Software can do that, though. You can't really understand this material, including the applications, unless you've got some level of understanding of what a limit is and what it isn't. So please try to spend some time on this section. My heart goes out to you. This is hard stuff. It's a bit of a bummer. It comes right at the beginning, right near the beginning of Calculus 1. But it's difficult stuff, and it's a necessary evil. The mathematical community itself struggled for years, like 100 years, to come up with the formal definition we'll deal with here. So speaking of, let's look at a little bit of the history. This is mentioned at best just in passing in the textbook. Isaac Newton in 1666 wrote a tract that included many of the ideas of this course, including the fundamental theorem of calculus. We'll cover that in chapter 5. It's part of Calculus 1. So you can kind of put your finger on the beginning of calculus. This is horribly oversimplified. But calculus really matures when Newton gets a hold of it. Newton, he's got a couple of birthdays reported. The Gregorian calendar came into existence sometime while Newton was alive, so it's his date of birth is sort of ambiguous as to whether you use the Gregorian calendar or the old Julian calendar. Now, there's a bit of historical disagreement between Newton and Leibniz. Gottfried Wilhelm Leibniz, he publishes a paper, 2 papers on calculus. Now, Newton's the first. He wrote a tract, memoir, but he didn't publish it. Leibniz, in 1684, he publishes a couple of papers that introduce calculus. So, in hindsight, the history's understood. Newton's first to do the work, but he doesn't publish it. Leibniz is first to publish, and that's the real punchline of this story. However, Newton and Leibniz get into an argument that goes on for years over who deserves priority for the discovery or invention of calculus, depending on your philosophical tastes. I used to teach honors enhanced calculus 1, and we'd go through the book, The Calculus Wars, as a little supplemental reading and look into the history of this. In the end, Newton ends up winning the calculus wars because Leibniz died and Newton kept at him. But the simple version is, yeah, Newton was first to do the work. Leibniz was the first to publish. Now, I should comment, of course, all this didn't happen in a vacuum. Calculus ideas, slopes of tangent line ideas, those had been around pre-Newton. In fact, Archimedes in 250 BCE does some work intimately related to concepts of integral calculus. Things we'll cover in, I think it's in chapter 4 when we get to the integral calculus stuff, maybe chapter 5. So there's these ideas are out there in the intellectual community, but there was a long raging battle between Newton and Leibniz. Now, the type of calculus Newton and Leibniz did, and certainly the type of calculus Archimedes did, these are not the kind of calculus we're going to do in Calculus 1. It wasn't clean, rigorous calculus. The stuff we're about to do, you can credit to Augustin Louis Cauchy. And his work's going to date from the 1800s, probably about 1820 is when a lot of Cauchy's work relevant to what we're about to look at when that was done. It's Cauchy that makes the informal ideas of arbitrarily close and sufficiently close more formal. So this is how we talked about limits, in particular in the previous section. Yeah, we're going to formalize that, and we're going to do it the way Cauchy did it. So calculus grows from kind of an informal, touchy-feely, certainly non-rigorous approach in the 1600s and the 1700s. And when Cauchy gets a hold of it, it becomes a clean, rigorous area of math. Some of the stories are spelled out in the Origins of Cauchy's Rigorous Calculus, a book that dates from 1981. It's still in print as a Dover book. That means it's available as a little inexpensive paperback book. But the calculus we're doing in this section is certainly based on Cauchy's ideas. These ideas are presented as a more central theme in a senior level class, Analysis 1 and Analysis 2 at ETSU, would delve into the definitions and deal more with the rigor and a real analytic approach to these ideas of limits and derivatives and integrals and sequences and series, and even what the real numbers are. We've been elusive on that, though there's some material in the appendices about what the real numbers are specifically. But we've got really no choice but to go through the definition of limit. We'll prove some things as far as a Calculus 1 class and taking tests go. These are arguably a bit peripheral. We're trying to get you trained to understand the ideas and do the manipulations. Okay, so we left off with an idea of arbitrarily close and sufficiently close and trying to pass through a point. Let's look at an example before we get to the formal definition. So let's go to the supplemental notes. Okay. And trying to motivate what we'll see is the formal definition. Consider the function y equals 2x minus 1 and x near 4. It seems intuitive that if x is close to 4, then 2x minus 1 is close to 7. I could draw pictures. We could argue about graphs of functions trying to pass through points. Certainly, this is plausible, and we've stated some claims. Hey, it's a polynomial. The limit certainly should be what we get by substituting in. But remember, those claims are based on this formal definition that we're about to see in this section. So we're going to play the following game. How close to 4 does x have to be so that y, 2x minus 1, differs from 7 by, say, less than 2 units? Okay, 2's not that close, but for the sake of illustration, I want to make the y value within 2 units of 7. How close does x have to be to 4? So that becomes the question. Here we go. Okay, we use absolute value to measure distance along the real line. Some comments about this, speaking of the appendices, in Appendix A1, there's some comments that absolute value is how you measure distance along the real line. So the distance between 4 and x is the absolute value of x minus 4. The difference between y and 7 is the absolute value of y minus 7. So this question about how close becomes a question about how small does this absolute value have to be? How small must the absolute value of x minus 4 be so that the absolute value of y minus 7 is less than 2? Do you believe? That's the same question we have up here. How close to 4 does x have to be? That is, how small does this have to be? So that y differs from 7 by less than 2 units. That is, the distance from y to 7 is less than 2. The absolute value of y minus 7 is less than 2. So these mean the same thing. It's made it more quantitative, and now we can do some algebra to deal with it. Well, y equals 2x minus 1. So in our desire to make y minus 7 less than 2, we'll substitute for y the quantity 2x minus 1. And then our desire is to make the absolute value of 2x minus 1 minus 7 less than 2. Let's manipulate that. So let's see, minus 1 and minus 7, we can write that as 2x minus 8. Absolute value of is less than 2. We could factor a 2 out of the 2x minus 8 term to get a 2x minus 4 in the absolute value. Actually, we could divide both sides by 2. Maybe skip a step of arithmetic here, bring the 2 outside the absolute value. It's positive, no worries. And cancel the 2's. And then we're left with the absolute value of x minus 4 is less than 1. Now, each of these steps is reversible. So if we make the absolute value of x minus 4 less than 1, then multiply both sides by 2 to get this, do some distribution and some rearranging, and we get y minus 7 in absolute value is less than 2, and that's what we were up to. So we need to make the absolute value of x minus 4 less than 1. We need to make the distance between x and 4, that is the absolute value of x minus 4. We need to make it less than 1. You make this distance less than 1, and that distance will be less than 2. We'll look at a graph here in a second, but here's the big idea. So it's going to work like this. You tell me how close together you want the function value from the alleged limit value to be. Okay, 2 is pretty big, but the numbers came out clean. Instead of 2 units, within a distance of 2 units of each other, what if we made it within a distance of 1 unit or 1/10 of a unit or 1/100th or 1/1,000,000th of a unit? The idea is we ought to be able to make the y value or the function value as close as you want to 7 if this limit statement is actually true. We ought to be able to make this quantity as close to 7 as you want by making x sufficiently close to 4. The as close as you want was the 2, and the sufficiently close is what we found out, turned out to be 1. When as close as you want is 2, sufficiently close is 1. If we were to change this to 1/1,000,000th, then we'd certainly have to change this down here. And in all this, we're going to say, I don't care what happens at x equals 4. Doesn't matter what happens at x equals 4. Okay, here's a graph. This is, if we can draw graphs, then it makes it more geometric. But here's what's going on, and we'll motivate our definition of limit using graphs as well. X minus 4, absolute value of is less than 1. Okay, here's 4. Absolute value of x less than 1 means the x values would have to be between here and here, be between 3 and 5. X is, well, 3 is less than x is less than 5. Take the absolute value, express it as an inequality. The information about this in the appendices as well. I think absolute values are dealt with in Appendix 1, A1. So saying this means the x values are between 3 and 5. I mean, that makes sense. They're within 1 unit of 4. Then the inequality y minus 7 is less than 2. Express it as an inequality without the absolute values. Solve for y, we get 5 is less than y is less than 9. Means y has to be between 5 and 9. Yeah, this was the within 2 units of 7 stuff that we had. originally. And then what we get in terms of a graph is this kind of thing here. So we get the absolute value of y minus 7 is less than 2, talking y values here. That means the y values for points on the curve have to lie inside this yellow band. And this will occur when the absolute value of x minus 4 is less than 1. That is, when the x values lie inside this blue band here. And they've shaded the intersection of the yellow and the blue is green. So what's happening then is if you have x values, input values in the blue band, then you're going to have output values in the yellow band. And we've got, what do we want? A distance of 2 here, and we ended up with a distance of 1 here. There's no coincidence that that ratio is the same as the slope of this line. If we're dealing with lines, this epsilon delta, this, how close would you like it to be? You tell me, and then I'll give you the sufficiently close. The ratio of those numbers, they were 1 and 2 in this example, is related to the slope of this line. We'll call them epsilons and deltas when we do this in a few moments. Now, what happens if you wanted the function to get closer to 7? Well, you'd make this little yellow band narrower. Instead of going 2 units up and 2 units down, you might go 1/10 of a unit up and 1/10 of a unit down. Well, then you'd have to narrow the width of the little blue band. And what you'd end up with then is a narrow yellow band, a narrow blue band, and a smaller little green box. And what's going to happen is that little green box is going to close in around this point 4, 7. And that's because the graph of the function is trying to pass through the point 4, 7. This is how the rigorous definition will meet my anthropomorphic definition. So make the yellow band narrower, you'd have to make the blue band correspondingly narrower. And it closes in around the point 4, 7. Yeah, notice, the graph tries to pass through the point. Yeah, in fact, it does. Irrelevant, though, in a limit question. Back to the notes. Okay. The ideas were to get function values close to limit values. That won't work for all x values, but if the limit exists and is what it's claimed to be, it'll work for certain x values if they're close enough to the appropriate value, the appropriate input value. Okay, in the formal definition of limit, we'll want to make this distance between function values and limit values arbitrarily small. We made it 2 in that previous example. Well, we'll want something smaller than 2. Now, here's an image for a given function. It's from page 76 in the book. So they've taken the same function and they've analyzed it for different distances. So what's happening in this figure is we've got a function that gets close to the value L when the input value X is close to an input value C. And we've considered the how close do you want it for different values. How close? Let's draw pictures for that distance of 1/10, 1/100th, 1/1000th, 1/100,000th, and then some arbitrary value epsilon. You'll get used to epsilon, Greek letter. How close? That close. How close must we make the x values to C to get the function values, these various distances of L? All right. And it is not to scale. You couldn't see it if it was to scale. So let's magnify the pictures. I lose some of the verbiage, but that's probably not a bad thing. And here's what we're up against. Okay, so we've got this function, same function, each of these graphs. We want to get within 1/10 of this value L. The question is, how close do the x values have to be to C to get the y values within 1/10 of L? That is, within this yellow band. Well, look at this. We can go as far right as here, and we'll still have the function lying inside the yellow band. We go as far right as here, then we get the function lying inside the yellow band. So we can extend to the right this far. You go any further and then, oops, the function is no longer within the yellow band. It's went out the top of the yellow band. And that's no good. We wanted the function values to lie inside the yellow band. To the left, we can go this far to the left. And here's where the function comes out below the band. So between this input value and this output value and this other input value, we get the function to have output values that lie within the yellow band. I don't know, it might turn around and come back down and lie in the yellow band somewhere far away. I don't know what the graph looks like. I'm interested in what happens close to C. What happens at C? Okay, we're talking about limits. It doesn't matter what happens at C, because we're going to address a limit as x approaches C. For the sake of a picture, actually the function's not defined at C because they poked a little hole in it. Hey, this function tries to pass through the point C comma L, right? Right. Okay, so if Dr. Bob's anthropomorphic limit holds, then the limit must exist and it must equal L. But to get the function to lie in this yellow band, we'd have to have input values between here and here. So it's not symmetric. We can go further to the left than we go to the right. We're going to ask the question in the sense, how close must x be to C so that function values lie in the yellow band? So I'm going to use the same distance to the right as I do to the left. It's going to be a question, how close to C must x be? Well, it needs to be this close on the right-hand side. On the left-hand side, it could be a little bit further away, but I want that symmetric behavior. How close to C? You need to tell me that. I need to tell you that if you've told me you want this distance to be 1/10. I tell you, you need to make this distance down here this. The distance from C to whatever we have here. Let's call it delta sub 1/10. So using these delta, lowercase Greek letter delta, 1/10, because it corresponds to the distance 1/10 over here. So you can go that far to the right. If you go that far to the left, you've still got the function lying inside the band. And we've done this distance measuring in a symmetric way. So if you'll choose, numerically, whatever this is, this to be delta sub 1/10, then if x minus C is less than delta sub 1/10, whatever that is, then we're going to have the function to lie within the yellow band. You go any further on the right, you got a problem. You could go further on the left, but it's the symmetry that we want to express distances from C that constrains us to choose the smaller of the distances on the right and the left. Let's do it again. Make the desired distance closer, smaller. Change it from 1/10 to 1/100th. Certainly not to scale in the picture. That produces this yellow band. It's narrower than the previous yellow band. How close you're going to need to get to C? Probably a little bit closer. Well, we'll see how far to the right we can go. So we'll follow the curve until it exits the yellow band at the top and follow the curve till it exits the yellow band at the bottom. So we could go this far to the right or this far to the left. My printer's going insane. Choose the smaller of the two distances. And let's call that delta sub 1/100th. So we can go this far to the right because of the shape of the curve. Let's go the same distance to the left. We're okay. We could go further to the left, but we want the symmetry. And for these input values inside this blue band, we'll get output values inside this yellow band. And we've drawn the intersection of those two. The book's drawn that as a little green box. Let's make the desired distance smaller still. Let's make it 1/1000th. Okay, now you know the story. I got the yellow band. I'll project back and see how far we can go from C and still have function values in the band. I can go a little bit further to the left than the right because of the shape of the curve. It's steeper on the right than it is on the left. That's why we're getting the non-symmetry in the intersections. But we can go this far to the right, the distance from C to this parameter here, that'd be delta sub 1/1000th. And you go the same distance to the left, and you're good. 1/100,000th, same picture. Yellow strip is narrower, correspondingly the blue strip is narrower, and the little bitty green box is smaller. Hey, look at that. That little bitty green box is closing in around a point. This is what makes Dr. Bob's anthropomorphic definition of limit work. The function is trying to pass through that point C, comma, L. And when you make this desired distance along the y-axis smaller, probably, the distance along the x-axis is going to have to be made smaller to follow the rules of I want the input values from the blue strip to produce output values in the yellow strip such that the function lies within the yellow horizontal strip. Then that function is going to get awfully close to the point C, comma, L. It's going to try to pass through the point C, comma, L. That's the reason Dr. Bob's anthropomorphic definition of limit works. It describes the graphs correctly when limits exist. And they call this, the book describes it as a challenge. Okay, suppose they gave you a little distance epsilon. Then how close would you have to make X to C in order that the graph of the curve lies inside the horizontal band for the corresponding input values? And we've illustrated that for several distances. 1/10th, 1/100th, 1/1000th, and so forth. All the pictures look the same. So with a given desired distance between f of x and L, just to note that epsilon, as they did right here at the end, the Greek letter epsilon, describes the yellow horizontal band. We want the function to lie inside that yellow horizontal band. We want to find a corresponding distance between x and c, denoted delta, as we had subscripted deltas above, Greek letter delta, both of these lowercase Greek letters, such that when the absolute value of x minus c is less than delta, we have the absolute value of f of x minus L is less than epsilon. Can you describe that a little less nebulously? Yeah. When the distance from x to c is less than delta, then the distance from f of x to L is less than epsilon. Can you do it even more geometrically? Yeah. When the x values are in the blue band, the y values corresponding to them are in the yellow band. That is, the points on the curve lie inside the little green box, the intersection of the blue and the yellow bands. So there's a geometric way to describe it. Think of these as distances. Arguably, that's also a geometric way. And we're going to deal with it in terms of algebraic manipulations as well. So we'll have algebra, we'll have geometry, we'll have distances underlying all of this. This concept of limit is certainly related to concepts of distance. Okay. Geometrically, these two conditions mean, there's an alternate way of describing it, means that the graph of y equals f of x intersects the vertical sides of the little green box, where the horizontal and vertical bands intersect, the intersection of the little bands, and does not intersect the horizontal sides of the little box, except maybe at the endpoints. So let's look at that again. So this has worked. Like I said, all the pictures look alike. May as well look at the biggest one. What happens is this works when the graph of the function intersects the horizontal sides of the little box, not the vertical sides, unless it does it right at the corner. And we chose these where we did have the intersections right at the corner each time. But I couldn't have this curve intersect the top of the box inside, between the corners. And if this curve came up more steeply and it did something along these lines, then no good. It's outside of the yellow band. So geometrically, how the graph of the curve has to intersect the little green box is it's got to intersect the horizontal sides. It can do it at a corner, but it can't do it along the top or strictly along the bottom. Over here, it went out the side. And I could have made these delta sub 1/10. I could have made that even smaller and we'd still have that kind of behavior. I mean, you'd get a less of the curve, but you'd still have the curve lying inside the yellow band. Geometrically, you've chosen the biggest delta value possible when you get it intersecting a corner like that. And we'll usually choose the delta values like that. It'll come naturally out of the algebra. So we get this kind of behavior in terms of intersections of the little green box. We've chosen deltas that couldn't be any bigger. If I made them bigger, we produce bad function values. We had looked at that. As epsilon is smaller, the deltas have to be made correspondingly smaller. And we get that little green box. That little green box, when you make the delta, when you make the epsilon smaller and the delta is correspondingly smaller, that little green box is going to center in on that point C comma L. I don't know if that's a point on the graph of the function or not. It doesn't matter if we're talking limits. But that little green box is centering in on what the limit will be when the limit exists. That's the reason the graph of the function tries to pass through the point C comma L. That's the reason Dr. Bob's anthropomorphic definition is actually correct. Okay, well, let's do it. So the motivation was all those pictures, the yellow bands, the blue bands, their intersection in a little green box, and requiring the function to lie within that yellow band, requiring it really to lie within that green box in a certain sense and intersect the sides of that box in a certain way. Well, here's the formal definition. So Augustine Cauchy says a couple hundred years ago, let f of x be a function defined on an open interval about C, except possibly it's C itself. This is old news, and we had this in the previous section. So again, this means the function's defined for x values close to C and bigger than C, close to C and less than C, but maybe not at C itself. We say that f of x approaches the limit L as x approaches C, written as we did in the previous section, if for every number epsilon greater than 0, there exists a corresponding delta greater than 0. Okay, this is what we were doing before. Arbitrary epsilon, and we'll choose a delta that works for the given epsilon, such that for all x satisfying the condition, the distance between x and C is greater than 0 and less than delta, or the absolute value of x minus C is greater than 0 and less than delta, implies the absolute value of f of x minus L is less than epsilon. In other words, f of x is within epsilon of L when x is within a distance delta of C. Oops, but not equal to C. Notice this 0 less than right there, highlighted in blue, says it doesn't matter what happens at C. Now, the function might not even be defined at C. Doesn't matter what happens at C. Now, I can say it formally because this is the formal definition of limit. So if anybody ever asks you to state the definition of limit, this is what they want. You're asked this on a test, this is what you're being asked, not that stuff we had about arbitrarily close and sufficiently close before. But this is related to that. We talked about f of x being arbitrarily close to L for all x sufficiently close to C. That's how we stated the informal definition. Well, that's exactly what we've got here. More specifically, the arbitrarily close is the for every epsilon greater than 0. The idea being we can make f of x as close to L as you want. Can't make it equal to it necessarily. Maybe we can, maybe we can't. But we can make it as close as you want. You tell me how close you want it to be. You pick any positive distance. We can get it that close if the limit exists by making x within, there exists a corresponding number delta, making x within a distance of delta of C. So the delta is the sufficiently close, and the epsilon is the arbitrarily close. The idea is epsilon could be anything. But the game is played as you give me epsilon, and then I got to run find delta. Actually, I'm going to turn the tables on you. I'll give you epsilon. You're going to have to run find delta, such that the definition works. The book states this as, here's epsilon. The challenge is to find delta such that the definition is satisfied. And we'll go through some examples on that kind of thing. Actually, we did one where epsilon equals 2 a while ago. Okay, more stuff about the little green box. All right, the book gives a picture, figure 2.17. I don't really care much for. It is accurate to say when the limit exists, we've got for a given epsilon, a corresponding delta such that when we choose x values between c minus delta and c plus delta, that is x values within a distance of delta of c, then we get output values, we get function values within a distance of epsilon of L. That is between L minus epsilon and L plus epsilon. So this is the picture from the book. I would prefer to actually draw the graph of the function. And instead of referring to f of x lies here and x lies there, draw the little horizontal and vertical bands. So I want to say, you give me epsilon greater than 0, then that determines a horizontal band. Now I got to run through and find a distance delta such that when I draw the little blue band, we get the desired kind of behavior. I've got the function lying inside that horizontal band. We get intersections of the horizontal side of the little green box here, and we get intersection of the horizontal side of the little green box there. That delta, it'll work. Could you make it bigger? If I made delta bigger, we might move over here and get some bad values that weren't between the yellow, weren't inside the yellow band. I can certainly make it smaller though. If I make delta smaller, it'll still work for this given epsilon. Think in terms of pictures in little green boxes and you'll probably be okay. We don't require that f is defined at c. I've said this before, but now I can point to an explicit place in the formal definition of limit. It doesn't matter what happens at x equals c. You said as much in the definition right there. When you said the absolute value of x minus c is greater than 0, you said x doesn't equal c. So I don't care what happens at c when taking limits. What matters is the x values close to c. What do you mean by close to? That's the stuff I mean by close to. All this epsilon and delta stuff. That's the whole close to story. And as commented, yeah, it took the math community about a century to come up with this clean definition. So it's pretty hard stuff. Conceptually, it's pretty complicated. But I've tried to draw you pictures and streamline it for you as best I can. So yeah, these ideas of closeness and sufficiently close and arbitrarily close and what close means, it's the epsilons and deltas that give you those closeness ideas. Now, I'm not sure I should even mention the following, but you're probably going to hear it somewhere out there. So let's clear the air. You may hear limits described in terms of a function that gets closer and closer to a limit value. You might even hear it said it gets closer and closer, but it never gets there. Yeah, that's just wrong. It's wrong, wrong, wrong. Many of the limits we see will behave in a closer and closer, but never gets their way. Also, many of the limits we see won't behave like that. So it's not a matter of closer and closer, but never gets there. That's simply not what a limit is. Maybe you've heard asymptotes described that way. Yeah, that's pretty much not what an asymptote is either. It's certainly not what a horizontal asymptote is in general. We'll define asymptotes using limits, so you came to the right place. It's not about getting closer and closer. That's just not what limits are. If you want to describe it informally, it's not closer and closer, and it's certainly not never gets there. It's about, if anything, it's about getting close and staying close. You tell me how close you want to get. That's epsilon greater than 0. And I'll tell you which x values will get you that close. And this will work for all of them x values. That is, I'll find delta for you. And if you take x minus c, an absolute value greater than 0 and less than delta, throughout, that's the staying close. For all those x values, that function will be within epsilon of the limit value L. If anything, it's about getting close and staying close. When we talk asymptotes, this getting close and staying close thing will be a little more appropriate. And it is all informal stuff. It means what it says with the epsilons and all that stuff. There's no constraint on the function taking on the value L. It can get there. In a pre-calculus class, if you had a thorough version of a pre-calculus class and you talked about asymptotes, they might have made a big deal about the fact that, yeah, the function, you can get there. That's not what an asymptote is the not getting there thing. Same thing in here with the limits. It's not something you don't get to. Maybe you do get there. Maybe the function is defined at C. Maybe it tries to pass through the point and it succeeds. That has nothing to do with limits. It could get there. Forget the never gets there thing if that's part of your math background. Well, part of your background, because it ain't math. It's wrong. There is a prohibition against x taking on the value c in a limit. So we've said 0 is less than x minus c. That means x doesn't equal c. The x equals c value is not part of the story of a limit. X equals c is not part of the story of a limit. X close to c is the whole story. And how do you define close to? Well, sorry about this. It's all that stuff with the epsilons and the deltas in the formal definition. If only all we had to do was look at x equals c, we wouldn't have to go through all this stuff. All right, so let's further dissect the definition of limit. Let's do a proof. Before we do, let's look at the formal definition again. Trying to illustrate the logic now behind all of this stuff here. Okay, to show a limit exists, well, first we'll have to make sure the function exists at appropriate places. And then we'll have to show for every number epsilon greater than 0, so we won't have any control over that. We'll just have epsilon greater than 0. Could be anything. It could be little, it could be big. The idea is it's small. Then we'll have to go find a corresponding delta such that this inequality implies that inequality. So the logic will go. We're given epsilon greater than 0. We'll choose a delta greater than 0, secondly, and then we'll show this. So I want to illustrate that logic. We'll show if this occurs for the x values, then it implies, then this occurs for the y values. That's the plan. Let's do it in exercise 2.3.a. So I made this one up because it's got a letter as part of its title. It says prove for f of x equals mx plus b, let's assume m is not 0, that the limit as x approaches a of f of x equals f of a. So if you've got a line, then you can evaluate a limit just by plugging in the a value. It says f of a, which would be what? ma plus b. All right, first, we need to make sure that f is defined on all of the reals. Sure, it's, we need to make sure it's defined on an open interval. Well, it's defined on all of the reals. mx plus b, it's a straight line. It doesn't have slope 0, I guess, because we were given that. But it's a straight line if the domain is all real numbers. So it is defined on an open interval containing a. It's defined everywhere. All right. So let epsilon be greater than 0. We don't have any control over that. Arbitrary epsilon greater than 0. We need to find a delta greater than 0 that satisfies the conditions of the definition of limits. If the x values are something or other related to delta, then the function values are something else related to the epsilons. We expect the delta probably to depend on the epsilon. If epsilon is big, you can probably choose a relatively big delta. If epsilon's little, you're probably stuck with a really tiny delta value. Let's take delta to be epsilon divided by the absolute value of n. For now, never mind where that came from. Just trying to illustrate the logic of the definition. All right. Hey, we divided by the absolute value of m. M is not 0. We didn't divide by 0. That's why I gave you that as a hypothesis. And indeed, delta is positive. Epsilon's positive. We've divided it by something that's positive. So the delta value is positive, and that's a legitimate attempted value for delta. Let's see if it works. Again, never mind where that came from. We'll take care of that soon enough. Right now, I just want to illustrate the logic of we're given an epsilon greater than 0, and then we choose a delta value. I'm choosing that delta value because I've been doing this a long time and I know it works, but we'll illustrate how to find them. Okay, then we need to show that 0 less than absolute value of x minus c, in this case, the limit value is a, so absolute value of x minus a, is less than delta. 0 less than that absolute value less than delta implies absolute value of f of x minus L is less than epsilon. F of x, well, that's what f of x is. It's mx plus b, okay. The limit is allegedly f of a. F of a would be ma plus b. So here's f of x. Here's the rumored L. We need to show this implies that. All right. The logic is step 0, make sure the function is defined in an open interval containing a, except possibly a itself. That's defined everywhere, not a problem. Step 1, let epsilon be greater than 0. You have no control over it. Step 2, choose a delta based on epsilon. More of that later. This is our choice of delta. And the final step, assume 0 is less than x minus whatever, absolute value of is less than delta. Show that implies f of x minus L and absolute value is less than epsilon. All right. Then suppose 0 is less than x minus a, x minus c, c equals a in this case, is less than delta. Now we had chosen a value for delta. We chose delta equals epsilon over the absolute value of n. So supposing this is equivalent to supposing this. Let's multiply through by the absolute value of m. It's an inequality. We're multiplying through by, it's actually two inequalities. We're multiplying through by something positive, and that preserves the inequalities. So we get absolute value of m times 0, which is 0. Absolute value of m times absolute value of x minus a. And yeah, the absolute values of m would cancel there. We've got something less than epsilon. Well, isn't that special? We're trying to show something is less than epsilon. Turns out this is the something, so it's going to work. Okay, so we've changed the supposition into this. We want to draw the conclusion, absolute value of f of x minus L is less than epsilon. We've got something less than epsilon. This something implies, we just dropped this left-hand part. The implication is valid. Don't bother that we've dropped a piece of our information. The implication is still accurate. We've only taken half the information, so the implication's good. Absolute value of m times absolute value of x minus a is less than epsilon. Let's tinker with that. We can take the absolute value of m inside the absolute value, right? It's the absolute value of m times x minus a. We can distribute, that's the absolute value of mx minus ma, still got it less than epsilon. And you wouldn't argue with the following in terms of validity. Motivation you might argue with, but validity, I can add b minus b in the middle of this. So let's take mx minus ma and write it as mx plus b minus ma. Because I added 0, so nothing's changed. Still got the absolute value less than epsilon. Why would I do that? Remember where we're going. Mx plus b, hey, mx plus b, that's the function. And what have we got here? We got, how about this? We got minus ma minus b. I could factor the negative out and write that as ma plus b. That's why we did the b minus b thing. Oh, mx plus b, that's f of x. ma plus b, that's f of a. So we've got f of x minus f of a is less than epsilon. Oh, that's what we had to show. So the limit exists, and the limit is what we claimed it to be. Step 0, function defined in an open interval about a, except possibly at a itself. Check. Step 1, let epsilon be greater than 0. Step 2, even though I started at 0. Step 2, choose delta. Never mind where it came from, but we chose a delta. Step 3, show if this occurs, then this occurs. And we did. And it was algebra that got us from this inequality to this inequality. And that's it. That's what it means for the limit to exist and equal this value, in this case, the f of a. So the logic is, at step 1, if you like, we took an arbitrary epsilon greater than 0, then we found a delta, and we based that delta on epsilon. It was epsilon divided by the absolute value of n is what we chose, which you might see some algebraic reasons why that worked in hindsight. But the logic was epsilon comes first and then delta. To the notes. Let's see, we've gone back to the definition. Where did we leave off? Right here. Okay. Example 2.3.a concerns a function whose graph is a line of slope m, and the relationship between epsilon and delta related to the slope of that line. That's not a coincidence. Look at example 2.3.2 in the book, in this section. They have a line of slope 5. And you know what? I bet you they choose delta to be epsilon divided by 5. The slope of the line and the boxes, the little green box, intimately related to the slope of a line, if the function is a line. If it isn't a line, this stuff gets even worse and more complicated, as we'll illustrate. Okay, we had made the following couple of claims in, I think, the previous section. We're starting now with the formal definition and building up a body of knowledge. We still need to establish some limit claims that we made in the previous section. We will. Use the formal definition of limit to prove the following. The limit as x approaches c of x equals c. So we're looking at the function x itself. And the limit as x approaches c of a constant function equals that constant. No surprises in either of those. But let's go through the formal proofs for those two things. And yeah, we had claimed that as an example, I think, in the previous section. Okay, so use formal definitions to establish these two things. Okay, so what do we got in this first limit? We got the function f of x is the function x. We're claiming the limit L is the right-hand side there, so L equals c. We've got x approaching c. Is this function f of x equals x? Is it defined on an open interval about c, except possibly c itself? Yeah, it's the identity function, they call it in the book. It's defined everywhere. So it's defined, here's an open interval, it contains c. The whole real line, negative infinity to infinity, written in interval notation, also explained in Appendix 1. So we're good on step 0. The function is defined on an open interval about c, except possibly c itself. It's defined everywhere. Step 2, step 3. Step 1, let epsilon be greater than 0, and then choose a delta. Let's choose delta equals epsilon, because I said so. You know, this is a slope of line 1. If we were to graph it, it's a slope of line 1, and we divided by the absolute value of the slope in that previous example. So you shouldn't be surprised to see that I take delta equals epsilon divided by 1, if you like. We'll get more practice on choosing the epsilon. It's still illustrating the logic. So we were given epsilon, we've chosen a delta. We need to show that if this occurs, then that occurs. And it's pretty easy on this one. It's easier than the previous one, in fact. 0 is less than x minus c is less than delta. We had chosen delta to be epsilon, so that's the same as saying 0 is less than x minus c, absolute value of is less than epsilon. Delta equals epsilon. Well, this implies the absolute value of x minus c is less than epsilon. Drop the 0 stuff. It's a one-way implication. I've taken only half of the information we had. Turns out that's all I need. Hey, what is x? That's f of x. So here's the function. C was the value we were interested in, x approaching c. Oh, excuse me. C was the L value. It's actually played two roles. I got mixed up. C was the L value. So we've got f of x minus L, f of x minus L, and absolute value is less than epsilon. X is the f of x function, c is the alleged limit, and we've shown that if this occurs, suppose this occurs, this implies f of x minus L, absolute value of is less than epsilon. That's what you have to show the limit exists and equals the L value claimed. And the L value claimed was C. So that happened awfully fast. That's kind of why I prefer to do that other one first. So now the reason this worked was we took an epsilon. We had an alleged limit value, L equals C. C plays two roles in this one, so don't be bothered by that. It's because it's the identity function. But we had an L value here. We went from this alleged L value up an amount epsilon and down an amount epsilon. Well, how far to the right and left of C can you go so that when you look at the horizontal box and the vertical band, and we get the intersection here in the little green box, that you get the line to cut through in such a way that, if you like, it intersects the horizontal lines of the little green box. And doing it at the corners is allowable. I take them to be the same. I go the same distance over as we went up. So epsilon and delta are the same. That's because this is a line of slope 1. Take this point right here, C comma C, and this point up here. If I were to compute the slope of that line, I'd do a rise over run thing. How much did you rise? Epsilon. How much do you run? Delta. So we got epsilon over delta is the slope of this line, and the slope of this line is 1. Well, if epsilon divided by delta equals 1, then epsilon equals delta. It's the slope of the line that determines the relationship between the epsilons and deltas. If this was a steeper line, I'd have to take the delta values, smaller than the epsilon values? Is that what it is? I have to think about the geometry a little bit. But the slope is certainly going to affect the ratio of the lengths of the sides of this box. And the lengths of the sides of this box are related to the epsilon dimension and the delta dimension. The yellow band's width and the blue band's width. So when we have lines with non-zero slopes, it's easy to go through and figure out the epsilons and deltas. When we have functions more complicated than lines, it's a bit more of a chore, as we'll see. Part B dealt with a constant function. Is there an interval about C where the constant function is defined, except possibly at C? Yeah, it's constant everywhere. Take the whole real line. So we do need to do this step 0, I've been calling it, to confirm that the function is defined close to C. Yeah, it's defined everywhere. We're good. We'll let epsilon be greater than 0, and we'll choose delta to be something. Trust me, delta equals epsilon works. We'll draw a picture. You'll see I could have chosen anything for delta, it turns out, as long as it's positive. Suppose 0 is less than the absolute value of x minus c is less than delta. Then k minus k, let's see, this k I want to say is f of x, and this k I want to say is L. So we've got f of x minus L when we've got k minus k. That equals 0, yeah, it's a constant function, and that's less than epsilon, because epsilon was positive. F of x minus L is less than epsilon. That means the limit exists. All right, this one happened even faster. just why maybe this is almost misleadingly simple. There was hardly anything to follow. Yeah, well, here's the picture. And the question becomes, here's the limit value k, it's a constant function. I want to make the function within epsilon of k. So I want the function to lie in this horizontal yellow band. What does x have to be? Well, as a constant function, it's always going to lie in the horizontal band. Did I say it correctly? What do I want delta to be? How wide does the blue band have to be? Well, it doesn't matter. The function's always going to lie in the horizontal band. We chose delta equal to epsilon. We could have chose delta to equal 7. We could have chose delta to equal 700. And this horizontal line would still lie inside that yellow band. And we'd still have the correct picture. We've got the graph intersecting whatever little green box you draw on the sides and not on the top. Although the corner would be allowable, it never intersects the top or the bottom. It's a constant function. So there's maybe some loose ends from the previous section in terms of now using the rigorous definition to deal with establishing these two limits. We got more stuff to establish. We had the 7 or 8 limit rules from section 2.2. And we'll go through, we'll establish one of them, I think, in the notes and refer to the appendices for some proofs of the others. Let's end the video there. What we're going to do next at the start of the next video will be to deal with functions that aren't lines and then see how you choose the delta values when you don't have a straight line. So those are more complicated. If you've got graphs, they're not too bad. Little word of encouragement. Hang in there. This is conceptually complicated stuff. I'm trying to streamline it for you and make it somewhat intuitive and make it somewhat mechanical in terms of how you go through for a given epsilon and choose a delta. I will see you shortly, and we'll start the second half of section 2.3. We'll do a bunch more examples, and then we'll finish up this section. And then we'll move on, and things become somewhat more mechanical. Chapter 2's got a fair amount of theory in it, but we'll do some more mechanical things and more evaluations of limits. Have a nice day. I'll see you soon.